Hello there, welcome back to the video lectures of engineering mechanics. So far we have discussed when a particle is moving in a curvilinear path, and we analyzed the field parameters with respect to the force and the acceleration by using the D'Alembert principle. We have developed the equation of motion. The next one, equations of dynamic equilibrium, we have developed. Right? So on this basis, we are going to be taking some of the working concepts on the curvilinear path. Then what is the working concepts here? Because as we know, some of the facts we are going to be discussing at the moment to understand better to solve this problem. There we can see here the working concept. Well, the first assumption is that the curved path is going to be the frictionless. The curved frictionless path, the particle is going to be traveling along the curved path. So there we can see, so there is going to be a plane of motion. One word we are using, the plane of motion. So what is the plane of motions? That's we are going to be discussing now. There we can see that curved path may exist on the vertical plane or maybe in the horizontal plane. So there we have seen the real example also. When we are moving on a horizontal plane, suppose we are moving on the road. So these concepts are going to be helpful to you when we are going to be taking the curvature either leftward direction or maybe the rightward direction. And these kind of examples when we are moving in a curved path in this way, right? These are when the moving in the horizontal plane, but the road is going to be like this. So then we are going to be using. So then what else? So if the plane motion where the particle is going to be moving in a respective plane, we are going to be say that is going to be the plane motion. So then what else we are going to be discussing? So here the first concepts I am going to be discussing over here. The first concept here we are going to be seeing. As you know, can you see? Now I am going to be taking certain parameters over here for the discussion. There we can see this is going to be your particle P. Right? So then what will happen? The particle is going to be trying to move towards in this direction. So it is trying to cover this way. Then what will happen here? The tangential acceleration is going to be acting in this direction. Right? At the same time, normal acceleration is going to be I am taking in this direction. That is the AN. Similarly, the weight of the component is going to be acting in the downward direction. That is the mg I am going to be saying. Or simply I am going to be say the weight of the particle is going to be the W. Right? Now come to this point. This is going to be the vertical plane and how the particle is moving in a curved path. These parameters we have seen. Now can you see here? This is going to be your horizontal plane where we are moving in the horizontal plane on the road and taking the left curve or right curve suppose. So in this case, can you see this is going to be the center of your radius of the curvature suppose I have taken. So then now you tell me how the weight of the particle is going to be acting over here. Is it moving in the horizontal plane? No, it is moving in the vertically downward direction. Thus I am going to be taking vertically downward direction. Can you see the W is going to be acting along the plane, but in this case it is acting normally to the plane of the motion. And now can you tell me the particle is going to be trying to cover this is kind of the distance. That means that kind of the path. So here is going to be your tangential components AT I am going to be say, and normal components I am going to be taking AN over there. Right? So that AN I am going to be taking to the out, I will write AN there. Now I hope you are able to understand. By the discussion over there, I am going to be writing here the first one is going to be weight of the component. So when a particle is moving in the vertical plane, then where is the weight is going to be acting here? That is acting in the plane. So the weight of the particle, when the particle is moving in a vertical plane, the weight is acting in vertical plane. But when it comes to here, the weight of the particle when they are moving in the horizontal plane, it is going to be weight is acting normal to the horizontal plane. Here the horizontal plane is nothing but the plane motion. The plane of motion. That's we have seen. So that means one is going to be acting in the plane one is going to be acting normally in the downward directions. This is going to be the first concept we have discussed. Now can you see here, there is another component AN is there. What is the AN? AN is nothing but your normal acceleration. There we can see AN, I am going to say, where it is acting always, it is acting towards the radius of the curvature, right? The center of the radius of the curvature. AN acts towards center of a radius of curvature. So there we can see AN always acting towards the center. Can you see? Even though it is acting in the vertical plane or in the horizontal plane, but the center it is going to be acting towards the center. And then the formula I am going to be using, AN is equal to the formula V square by rho. I am going to be using this equation already we derived in the previous video lectures. So the first one where it is going to be acting, the second one AN, that is going to be normal acceleration where it is going to be moving towards the center, right? So here is the third point. As we observe that the radius of the curvature always it is going to be the maintain the constant. Then directly we can take the radius of the curvature. But in some cases the radius of the curvature is not constant. It may vary. So then how could you develop the radius of the equation? So the radius of the curvature, that is equal to, so we are using the formula that's going to be 1 plus b square y by dx square. This is going to be whole square into 3 by 2 we are going to be taking here, and divided by d square y by dx square we are using. By using this equation, we can find out the radius of the curvature. If radius of the curvature is constant, there is no problem, directly we can take it. But when it is not going to be, it is changing with respect to x, or the y component is changing with respect to x. So it means that the curvature path, the curved path radius is not the constant. By that, we can using these equations to find out. What is the last one? The fourth. The working concept. What is the fourth working concept here? We are going to be talking about the AT. AT is equal to, we are going to be say dV by dt. It is always, at any instant of the time, we can calculate the tangential acceleration. So, if the velocity is going to be constant throughout the system, then AT will going to be 0. If velocity is varying from the point to point, so then what will happen? We are going to be getting your tangential component. So this is going to be different working concepts we have discussed. What are the points we have discussed here? The first one is going to be the weight of the system. When the weight of the system means when the particle is moving in a vertical plane, that is going to be the vertical plane of motion. So then the weight always acting in the plane. But when it is moving on the horizontal plane, that means the plane of motion is in the horizontal direction, then the self weight is going to be always acting in the downward direction. That means normally to that plane. That means this is going to be your curved path and your self weight is going to be acting in the downward direction. And the third point is going to be the second point is the normal acceleration. It is always acting. Suppose this is going to be the point, your normal acceleration, suppose this is the point, means your normal acceleration always acting in this direction. Right? The tangential acceleration is going to be acting always in this direction. Right? So when normal acceleration, it is always towards the center of the radius of the curvature. That is the second point. The third point is that when the radius of the curvature is going to be not the constant, so then by using this equation, we will find the radius of the curvature. In the fourth point, we are discussing about the tangential acceleration. So in the tangential acceleration, when the velocity is going to be constant throughout the curved path, then your tangential component will going to be 0. But the velocity is going to be varying. By using this equation, we can calculate the instantaneous the tangential acceleration. I hope you people are able to understand what we have discussed here. These are all the parts of the kinetics we are going to be discussing when a particle is moving a curved path. Still, you feel any difficulty or if you feel any confusion regarding the concepts, and please put in the comment section so that I can reach you. Thank you for supporting me and for better understanding, please follow the series of video lectures so that your understanding capabilities are going to be a little better. Thank you.